Problem 14. 1 mole of an ideal diatomic gas goes from A to C along the diagonal path as shown in the figure. The scale of the vertical axis is set by P of AB, which is equal to 5 kilopascal, and P of C, which is equal to 0.5 kilopascal, and the scale of the horizontal axis is set by V of BC, which is equal to 4 cubic meter, and V of A, which is equal to 2 cubic meter. During the transition, what is the change in internal energy of the gas and how much energy is added to the gas as heat, and how much heat is required if the gas goes from A to C along the indirect path ABC. So here we have to see the PV diagram, and in this PV diagram pressure is in y-axis and volume is taken in the x-axis, and the pressure at point AB, which is given here as 5 kilopascal, and pressure at point C, which is equal to 0.5 kilopascal in y-axis. Likewise, in x-axis, the volume at point B and C, as well as the volume at point A, is given here as 4 cubic meter and 2 cubic meter respectively. So here we have to answer for these three questions. So in the first question, we have to get the information about the internal energy change. So let's write the given first, and then we can answer one by one. So what is given in this question? From PV diagram, the pressure at point AB, which is equal to 5 kilopascal, which is 5 multiply 10 power 3 pascal. Likewise, the pressure at point C, which is 0.5 kilopascal, which is equal to 0.5 multiply 10 power 3 pascal. Likewise, in x-axis, the volume of BC, which is equal to 4 cubic meter, and the volume of A, which is equal to 2 cubic meter. So in the first part, we have to find the answer for the change in internal energy. And they clearly mentioned the gas here is a diatomic. So it's a diatomic gas. And also they gave the information about the number of moles of the gas here as 1 mole. And we have to first answer for the internal energy change. As we already studied from the theory, the change in internal energy is given by the rule NCV delta T. So if you expand this equation, we will get N of CV T final minus T initial. That means here you can see the gas undergoes the process from A to B and the B to C. But if you want to get the information, we can easily get the information from point A to C. So the diagonal of AC will give you the information about the entire process. So what I am going to do here, the information about temperature final and temperature initial is not given. So what I have to do, first of all, I am going to find the temperature at point A and temperature at point C. So temperature at point A is the initial temperature and the temperature at point C is the final temperature. So that means the initial point here is A and the final point here is C. The intermediate is the point B. So what I'm going to do, instead of going to point B, better we can solve this question based on the diagonal of A to C. Clear? So if you rearrange this, if you write the equation in terms of point A and C, we can write this term as N CV TC minus TA. So once we find TC and CA, we will get the answer for internal energy ECD. But the information about the temperature at point C and A is not given. So what I'm going to do, I'm going to apply the the ideal gas equation for point A and C. As we know, the ideal gas equation, which is equal to PV, which is equal to nRT. I'm going to use this equation for point A and C. So if you write this equation, what we will get? P of A, V of A, which is equal to nRT of A. So here A is the point they represent in the figure. Likewise, I'm going to apply the ideal gas equation for point C. This equation will become P of C, V of C, which is equal to N or TC. This is N or TC. This is our first equation. This is our second equation. From first equation, I'm going to rearrange this equation in terms of TA, which is equal to PA VA over NR. Likewise, from equation 2, we can rearrange this equation in terms of TC. So TC, which is equal to PC VC over NR. So now you can see in place of TC and TA, I'm going to substitute this value here. So by that, our internal energy equation will change as change in internal energy, which is equal to N CV. In place of TC, I have to substitute PC VC over NR minus, in place of TA, I have to substitute this equation PA VA over NR. So we take NR outside because these terms are common. It's a common term which is inside the bracket. So we can rewrite this equation as NCV multiplied by 1 over NR inside the bracket PC VC minus PA VA. As we know, this is the diatomic gas. So for diatomic gas, CV takes the value of 5 over 2 times of gas constant R. So what I'm going to do, in place of CV, I'm going to substitute this value. So by that, this equation again remodified as N multiplied by 5 multiplied by R over 2 multiply 1 over NR multiplied by PCVC minus PAVA. Clear? Now you can see we can cancel the term of NR as well as NR here. So by that, this equation is exactly equal to 5 over 2 times of PC VC minus PA. Now I'm going to take the value of the pressure at point C and volume at point C. Likewise, the pressure at point A and then volume at point A. So we have to get this value from the PV diagram. So the internal energy change, which is equal to 5 over 2 times. Let's we go back to the figure. So what's the value of PC and VC? So you can see PC value is equal to 0.5 kilopascal, and then VC value is given here because B and C have the same value. So the information is already given here. So we already write the given here. So from this given, we can take the value here. So now I'm going to substitute the value here. In place of PC, the value is given here as 0.5 kilopascal. So kilo stands for 10 to the power of 3 multiplied by VC. VC value is given as 4 cubic meter minus, and PA value is given as 5 kilopascal. 5 multiply 10 power 3 multiplied by VA is given here as 2 cubic meter. So we got all these value from the given, and also we can just see the information from the PV diagram. Clear? So here I am going to find the answer. Let's see what's the answer here. Here I got the answer as minus 20 kilojoules. So this is the answer for the first part. That means the answer for the A. Now we have to find the answer for B. What is given in the B? Let's we just go back to the question. We have to find how much energy is added to the gas as heat. So you can see, if you want to find the energy added to the gas, we can consider the area under the line of A and C, because the intermediate point we no need to bother. So we can just consider the area under this line A and C. So by that, all these area we have to consider. And if you see this area, we can just consider this as the area of the triangle and area of the rectangle. So this is area of the triangle, so area of the rectangle. Because why I just write, we already know the formula for area of the triangle and the area of the rectangle. By substituting the values in this, we will easily get the answer. So I'm going to find the area under the curve for getting the answer for part B. So let's find the answer. For part B, we are going to find the work done. So work done, which is equal to pressure multiplied by change in volume. And here the area under the curve from point A to C is area of triangle plus area of rectangle. As we know, the formula for area of the triangle is half multiplied by base multiplied by height plus length multiplied by width for the area of the rectangle. So let's just go back to the figure to get the information about the base and height of the triangle. So this is the base of the triangle. So I'm going to consider this value. This is the base of the triangle. This is the height of the triangle. So what is the base of the triangle? VC minus VA. So VC minus VA give the information about triangle base. So I can write it here. Half multiplied by VC minus VA. And what is the height? Height here is this point, right? So that means this value and this value, which is already given in the question. So point A as well as point C. So let's substitute the value here. Point A value here is 5 kilopascal. So 5 kilopascal, which is 5 10 to the power of 3 minus, or I can first write the formula. Pressure at point A minus pressure at point C plus length of the rectangle here is VC minus VA. That is a rectangle length, and then its width is this part, right? So that means, so this is 0. So what's the value? So PC value here is given as a 0.5 kilopascal. So we have to write the value for rectangle only. PC minus 0. So I'm going to substitute the value. Half VC value here is 4 minus VA value is 2, and PA value is 5 kilopascal, which is 5 10 to the power of 3, minus PC value is 0.5 kilopascal plus VC minus VA. So VC value is 4 minus VA is 2, and then this one is 0 to 0.5 5 kilopascal. So these are the values we take from the given. So let's see what's the answer. 1 over 2, 4 minus 2 is 2, and then this one is 4.5 multiplied 10 to the power of 3, plus this one is 2, this one is 0.5 multiplied 10 power 3. So let's see the answer. So here we can cancel this with this. So this one becomes 4.5 multiplied 10 power 3 plus 2 multiplied by 0.5 is 1. So 1 multiply 10 power 3. So the total is 5.5 multiplied 10 power 3 joules. So this is the answer for part B. So what we did here, we simply consider the area under the line of A to C. That is our diagonal. And for getting the answer for the last part, we have to find how much heat is required. So for that, we have to use the first law of thermodynamics. So as we already know, the first law of thermodynamics is given by the rule Q, which is equal to change in internal energy plus work done. So here, the internal energy we got in the first part, that means A part, is minus 20 kilojoules plus, and the work done here is 5.5 multiplied 10 power 3. So this is minus, this is positive. So 20 minus 5.5, which is 14.5. So 14.5 multiply 10 power 3 joules, and don't forget to put the minus sign. So this is the answer for the last question. That's it. Thank you.